we have some intuitive understanding of how the intensity of a wave, in particular sound waves you'll be familiar with, and light waves behave the same way, and you'll have some familiarity with that, about how the intensity of those things change as you get farther away from them. So if we think about a speaker, maybe a speaker in a car stereo, you can buy speakers that have a power rating of 5 watts. That means for every second that goes by, they'll put out 5 joules worth of energy. Actually, the way they measure it is they use up 5 joules worth of electrical energy. They put out some slightly smaller amount or maybe significantly smaller amount of sound energy. Some energy is transformed into heat, but regardless, they put out a certain amount of energy at a certain rate. So we can call that the power rating, the P, for the speaker. But not all of that energy makes it to your ear, because some of it we know makes it to your passenger's ear in your car, and some of it goes outside, and somebody walking down the street, they might be able to hear your stereo, especially if, say, your window is down. Some of that energy spreads out into empty space where nobody hears it. So a more useful quantity in terms of how loud that's going to sound to us would be the intensity. Now, intensity takes into account the power of that speaker, but it also takes into account the area over which that power has to be spread. So let's say we have a speaker right here that's putting out some sound wave with a power P. And then coming out from that, we'll just look at a few different points in space. So if I were standing at this position, that sound is at that spot where my ear is, but it's also at every other position the same distance away from that speaker as this spot. So the power is spread out over a circle, actually in 3 dimensions, over a sphere in space. And so I'm only getting the power that occupies this one little part of that sphere. And then if we looked at a point that's a little farther away, then the power is spread out over an even bigger area there. Well, that's a pretty lousy circle, but you get the idea. And so the intensity we can think of, intensity, we usually just use an I for this, but intensity is equal to the power divided by the area over which it's spread. Now, since waves like this travel out in 3 dimensions at the same speed in every direction, that power is, at any moment in time, spread out over a spherical shape. So the area we're talking about is the surface area of a sphere. So we usually write this as intensity is equal to the power divided by the surface area of a sphere, which is 4 pi r squared. So the idea here is that as we get farther away, as r increases, intensity is going to decrease with the square of our distance. So if we double the distance away from the speaker, the intensity decreases by a factor of 4. Then it's linear with power, so if we double the power, intensity is going to double at every point in space as well. The intensity equation then, we use units of watts per square meter for the units on intensity. That's just the power unit is watts divided by the area unit is square meters. And so this relationship, the I equals P over 4 pi r squared, is called the inverse square law because it's proportional to the inverse of the square of radius. The intensity is, and it applies really to any 3-dimensional wave. So this applies to light, it applies to sound, it applies to, well, I guess those would be the 2 main examples that we'll work with here. If we were dealing with something like a water wave, that energy mainly gets spread out on the surface of the water, and so we wouldn't be looking at a sphere over which the energy occupies. It'd be a circle, a ripple in the water. So it'd just be 2 pi r for the radius there. So that's in 2 dimensions. But in 3 dimensions, that power gets spread out over 4 pi r squared for the area. So we can use this inverse square law.